Good morning, everyone. Thanks for coming along today. It's great being back in London. I'm living in Chicago now, but I used to live here until fairly recently. So, I was at a talk by Dean Wampler a month or two ago, and one of the things he said was really focus on the fundamentals, because everything else around us will change. And that's something that really resonated with me and my approach to everything I've done in my career, on really understanding what's happening. So it's fine relying on some of the hidden magic, and we can get by with that. And, things may be fine today, but at some point, one day, we'll get tripped up by it if we don't really understand what's going on. So today, we're going to take a look at some of the core Clojure functions by way of looking at writing our own implementations of them. So see what we learn about them by writing them ourselves. So just a couple of quick questions first. Who's written their own implementation of some core functions within their own favourite languages? Okay, quite a few of you. Those of you who haven't, I'd urge you to go and have a look at this at some point after the talk and see what you learn by actually going through and seeing how they actually work in whichever language you're working in. Secondly, who writes much Clojure? Okay, so just a few of you. What we'll do is we'll start nice and slowly so that we can build things up and hopefully everyone can follow along. And a lot of the things we're talking about is going to be equally applicable in any language. So before we jump into the code, we're going to take a look from the view from 10,000 feet, which is something like this. And one of the reasons I've got this up here is I took the leap into software development after taking the leap from a plane, because I'm pretty scared of heights, and I thought if I can jump myself from a plane, I can probably switch careers as well. Anyone else skydived? Not all that many of you. I'd urge you to do that as well. It's a whole lot of fun. But for a moment, imagine that you have skydived, you've done it regularly, you know exactly what you're doing. As you're rushing at terminal velocity towards the ground, 10,000 feet below you, you're just feeling confident. You've packed your parachute, you know how it works, you feel fully in control as you're falling down. You know when you pull the chute, it'll deploy, and you'll nice, in control, take yourself to the ground. So you've done this plenty of times, you know exactly what's happening, you've got complete confidence in the equipment. But are you missing out on the ultimate thrill of a base jump? So a base jump, like a skydive, but instead of from a plane, it's from a fixed structure. So either a building, like in this case, or from a natural structure as a cliff or a mountain. So you're going to throw yourself off, and you're going to deploy a parachute in the same way. But as you're taking this jump, well, one, are you missing out on this because you don't think the equipment that you've got and the skills that you got from skydiving will allow you to do the base jump? Or are you just going and jumping straight in, assuming that everything works the same and you're just taking that leap of faith? So we'll come back to this a bit more in the end, after we've actually jumped into the code. But as we're going through this, just have a think. When you're writing your code, and every line of the code, do you feel fully in control? Do you know what's happening? So that's the question that we're asking today, and we're going to take a look at some of the core Clojure functions. And we're going to start with reduce. So this is fundamental to a lot of the Clojure sequences. There's a lot on here. We're going to break this one down. But what reduce is going to do is going to iterate through a collection and just reduce it down to a single value. It will have a function, an initial value, and a collection. And it can also work if we don't supply it with the initial value. But we're going to look at the case first, where we do supply an initial value, val, and reduce is going to return the result of applying the function to val in the first item in the collection, and then it's going to take that result and apply it to the next item in the collection, etc., etc. And if the collection has no items in it, we're simply going to return the val, and the function is not going to be called. So this is where we're going to start off, and we're going to build it up in a test-driven development way. When I was doing this, I used the speckle testing framework. So within the namespace for the test, so our reduce spec namespace, going to require in the speckle testing framework, and also require in the namespace where we're actually going to write our reduce function. And start off, simple test. We should get a result of 1 when we pass into our reduce function the addition function, an initial value of 1, and then just an empty collection. So if we call our reduce function with +1 and an empty collection, we should result in 1. So all we need to do in order to get this test to pass, we move to our namespace where we're writing our reduce function. We just need to define our reduce function, so myReduce, as being a function that has 3 parameters, the function, the initial value, and the collection. And in order to get this first test to pass, all we have to do is return the value. So exactly like the Clojure docs documentation for reduce said, if the collection is empty, we just need to return val without applying the function. So first test run, and that passes. So next obvious thing, have a single item within the collection. So if we stick with the addition function, an initial value of 1, and this time we have the element 1 within our collection, then this should result in 2. So we're just adding 1 to the contents of the collection. So we just need to put a conditional in this case. So if the collection is empty, then we're going to just return the val as before, the initial value. If not, we can just apply the function to the val and the first item in the collection. And that's all we need to do in order to get this next test to pass. So this will return 2 for us. We can then build it up when we have more than 1 item in the collection. So in this case, got a vector with 2 and 3 in. So if, again, we use the addition function, we reduce this and we should get 6. So we can keep the function the same at the start. So if it's empty, we're just going to return val. And we can iterate through by just recursively calling our myReduce function with the function, so addition in this case. And then val is returned as applying the function to val and the first item in the collection. And the collection is passed back as the rest of the items in the collection. So in that way, we're just iterating through our input collection, applying the function to the val and the first item in the collection, and in that way reducing it through. So this works. We've got another test working, and we can add more tests in order to look at different functions, different collections, and different input values. So the initial val. So this works, and we can build up a test suite for this. So we can then look at the situation when we don't have an initial val. So we just have our function and a collection. And this works just by applying the function to the first 2 items in the collection. So that will then give us the first result. And then we apply the function to that result with the next item in the collection, etc., etc. So test for this, we can just call our reduce function, staying with addition in this case, no initial value, and we have a collection, a vector with just a single value in. So this should return 1. In order to get this to pass, we can add in a second arity. So just with a function in the collection, no initial value. And what we need to do is call our reduce function where we now have val as being the first item in the collection, and we pass the rest of the collection as col. So we're just taking out the first item in the collection to become the initial value. This test passed because in this case we've just got 1 in the collection, so 1 becomes our val here. The rest is just the empty collection, and we know when there's an empty collection we just return val. So we get 1 as the result. And we can continue adding tests for this as well, where we have more than the one item in the collection. And we can build up our test suite to make sure that these still pass. And then there was the extra condition within reduce that if the collection contains no items, then the function must also accept no arguments, and the result for reduce is just returning the evaluation of the function with no arguments. So we can do this. We can write some tests. So got one here for addition. So if you pass the addition function to reduce with an empty collection, this should result in 0, because evaluating the addition function results in 0. And do a similar for multiplication, that returns 1. So in order to get this to work, we just need to modify our arity here. So put in the condition if the collection is empty. So if we've got an empty collection, we're just going to evaluate the function. Otherwise, we're going to call our reduce function where we've taken the first value of the collection out as the initial value and the rest as the rest of the collection. So that works. And that works for those tests. So a question for you. I've got a function that seems to be working. It's passing our test suite. How many tests is enough in order to be confident that our function does what we want it to do? 42. 42 seems a good number. Anyone else?
One for each branch or something?
One for each branch. How many branches? Okay.
I'm going to go with 3 because it's easier than 42.
3 is easier. I think at the point when I'd built this up, I'd got around about 10 or 12. And I was like, okay, it's doing what I want, but I know by a long stretch I've not looked at anywhere near all of the different Clojure collections and functions that we could put together. So, yep, it works. I'm fairly confident, but I'm not 100% sure. So I decided to look at some property-based tests and see whether this would help me out in my confidence of the work we've done. So in property-based tests, we're making statements about the expected behavior of the code across all of the domain. So rather than just individual specific tests. And those statements we can verify against some pseudo-randomly generated inputs. I'm not going to talk much about property-based tests because Aaron Bedra is going to cover that in the next talk. But I wrote these for each of the functions, and you can do that in Clojure with Clojure tests.check. So Reed Draper wrote this a couple of years ago. So it's a great framework for doing the property-based testing in Clojure. So this is what I ended up with just for the reduce function, but a lot of this code was reusable for the rest of the functions. So we can generate Clojure collections, and I was having generators of generators, so we're going to generate one of these Clojure collection types. So as an example, we can generate a vector, so an any size vector, and that vector will contain a generator of any Clojure values. So we can have any Clojure type, any Clojure collection type with any type of value that we can pass into our tests. So we can do this for vectors, lists, sets, etc. And then we can run this as a property-based test with as many tests as we like. So in this case, 1,000 examples. So for all of those, we're going to have a generator of collections and a generator of any Clojure values. And we can assert that our function that we've written, or my reduce function, behaves the same as the core reduce function. So we can just pass our generator of collections and our generator of initial values to a function. So I just wrote a simple function to pass into the reduce where we just from 2 values, we just take the second one so we can reduce through the collection in that way. And we put in an example, so if we just evaluate the function on its own, it's going to return a result, in this case true. So we've got a generic function that we can apply to our reduce function, and we can use our generated collections and generated initial vectors to pass into this. So in that way, we can run as many tests as we like and show over all of those collection types that the function that we wrote behaves the same as the core function. So I found this really useful. Use the TDD approach with the unit tests in order to build things up, and then use the property-based testing to complement that to give confidence that things are working as we thought they were. So what do we learn from doing that? How confident are we about switching from the skydive to the base jump? So a couple of things that stood out for me going through this. Reduce functions that require 2 arguments can be passed to reduce just with a single argument. So as an example, if we have a simple function that takes 2 parameters, x, y, and we're just going to return the sum of them, if we try to call this function just with a single argument, it would fail. But we can pass to reduce the function with just a single collection, and this is going to work. We don't need to pass the 2 arguments to it, because if there's just a collection, it's just going to return the first item, and it's not going to actually evaluate the function. So this will work. So we can pass functions that require 2 arguments just with a single argument to reduce, and this works. So this maybe gives us more power than we initially thought. We also know that we need care when we're using functions, when we're passing functions to reduce, that they will return a value if they're evaluated with no initial value in an empty collection. So we looked at the addition and the multiplication function when we had an empty collection, and that worked fine because you can evaluate addition and you can evaluate multiplication in Clojure. You can't evaluate the minus function, so this will fail. So if you're writing your own functions that are going to be passed to reduce, we need to make sure that we look at the case where you just evaluate the function on its own without any arguments. If there's any risk that we're going to have those edge cases where we have no initial value and no items in the collection. So if that's a possibility, we need to think carefully about how our function works and have something in place for how it can be evaluated just on its own. We'll move from reduced to counts. So fairly straightforward. It's going to return the number of items in a collection, and nil will also return 0. So that's what count needs to do. We can build this up in a TDD way as well. I'm going to start with 3 tests here. So if we have an empty list, it should return 0. Nil should return 0. If we have a single item in a collection, that should return 1. So we've got a few tests there that we can then start building our function on. So we can write our myCount function, takes in a collection. If that collection is empty, it will return 0. And nil also returns 0 for this. Else, we're going to return 1. So that's all we need to do in order to get that last test to pass. So if we've got an empty collection, 0, else 1. We can then build this up where we have more than 1 element in the collection. And we can do this by recursively building up the function. So if we have a recurse point here, we can start that with the initial collection and a result of 0. We can have our escape from the recursion when the collection is empty, and at that point we're going to return the result. So for the initial tests, we start with an empty collection, so we'll just return the result straight away, which is 0. Otherwise, we're going to recurse through with the rest of the collection, and we're simply incrementing the result. So this works, and you can have collections with as many items as you want, and we'll get the correct result. It doesn't look all that pretty, though. But now we've got a passing test suite, we can look to refactor this. And what we're doing within this function is we're just iterating through the collection, and we're reducing that down to a single value. So that sounds very much like the reduce that we just written. So we can refactor it with a function that we just wrote. I'm sorry. Get it the right way. Oh yeah. So with our reduce function. So our reduce function is going to take an initial value of 0. So if there's nothing in the collection, we'll just return 0, and it's going to take the collection. And the function that we're going to have has 2 arguments, so the result and the collection. But we don't care about the collection because all we're doing is incrementing the result. So we can just name our result, have an underscore for the second parameter because we don't care what that is in terms of the body of the function. So we can use our reduce function, iterate through the collection, and return the count. And this works. Again, we can use our property-based testing to give us more confidence that this function behaves the same as the core Clojure function. So given the same collection generator that we used before, we can just write our property-based test where we are asserting that our myCount function with our generated collections behaves the same, gives the same results as the count. Let's move on to filter. So filter will return us a lazy sequence. And that sequence will contain the items in the collection where a predicate is returned true. And that predicate must be free of side effects. It will also return a transducer if there's no collection provided. But for the talk today, we're not going to cover that. We're just going to cover the examples where we actually do pass a collection in. So we can start off with a test where we're just looking at an empty collection, and we have a function such as 0, but it could be pretty much anything in this case. And we expect that it's going to return a lazy sequence. So the class of our result is going to be a lazy seq. And it should have a count of 0 because we started off with an empty collection. We're filtered for something, and we're going to get an empty collection out. So we've got a couple of assertions in there. We can use our count function that we just wrote. And we can get this to pass by writing our filter function, which takes in the predicate and the collection, and we return a lazy seq of the collection. So the lazy seq is going to take in a body of expression, so in this case the collection, and it's going to return a lazy sequence, which is just going to be evaluated when it is first called, and then the result is going to be cached for any subsequent calls. Okay, so let's look at building this up recursively when we add more elements into the collection. So in this case, we've got the numbers 0 through 9, and we're going to filter for even ones. So we expect the result out a lazy sequence with 0, 4, 6, and 8 in. So we can build this up recursively. So we have a recurse point in here. And I decided, when first doing this, to start the result so that our collection of filtered items to be a vector. And that way, we could use conj to add in to the back of the vector everything that is past the predicate. So everything that's filtered goes into our vector, and then we can just convert that to a lazy sequence at the end. And that way I didn't have to worry about what the input collection type was and how conj works. I could just use the vector, and I knew that I'd get things in the right order. So when the input collection is empty, we're just going to return the lazy seq of the result. And until then, we're going to recurse through with the rest of the input. And if the predicate holds true for the first input, so the one that we're looking at, we're going to add that into our results vector. So we're going to conj the results with our first input. And if not, we're just going to return the result, so the vector that we're getting. So this test passes. And we can add more tests. And these can pass. But what's the problem with this? So we're getting the right result, but we're not actually doing it lazily. So if we convert it to a lazy seek at the end, but we're not actually doing the filter lazily, so we're not getting any of the efficiency benefits of running the filter in that way. And a reason for that is that conj behaves differently from cons. So conj in Clojure depends on the collection type to know how to work with it. So because of this, it needs to evaluate immediately. So it needs to realize the result immediately in order to know what to do with it. Cons is different though. Cons is always going to add into the front of the collection no matter what that collection type is. And so that can be evaluated lazily. So let's refactor this now using cons rather than conj so that we actually have our filter which is lazy. So in order to do this, we can, I'm sorry, wrong button. Let's start here. We can say if the predicate is true on the first item of the collection, what we're going to do is we're going to cons, so we're going to add the first item of the collection into the collection which contains all of the other items to come in that collection. So we're just adding into the front of everything to come. So everything to come is when we pass in back into my filter the predicate and the rest of the collection. So we're just building up recursively what's happening by adding into the front of everything that's to come. If the predicate is false, we're just going to recall my filter with the predicate and the rest of the collection. So that's going to continue whilst the seek on call returns true, and this will return true when there's an item in the collection. So as long as there's items in the collection, we will continue recursing through the collection. And then that result is passed to lazy seek. So we'll end up with a lazy seek of our result, and this time we've done it lazily because we're consing into the front rather than realizing each time with conj that we had before. So what did we learn before taking this plunge, this jump? Here's a question. How do we get a vector containing just the even numbers given this input? So a vector of the numbers 0, 1, 2, 3, 4, 5. So you may think just we can do the filter on even numbers on that collection, and that's fine. And this type of thing tripped me up when I was first looking at Clojure, because yes, that gives the right numbers, but it gives it as a lazy seek and not actually as a vector. So if you're wanting to do other things with it, still as a vector type, we need to take that result into a vector. So if you're getting the wrong type of data structure back than you thought, the way that filter works, returning a lazy sequence could be a reason for that. So that was filter. Let's move on to map. Map, again, is going to return a lazy sequence, and it's going to do that by applying the result of the function to the first items in all the collections, followed by applying the function to the second item in all of the collections, etc., going through. And the map can take any number of collections. Again, it's got an option where it doesn't take any collections and returns a transducer, and we're not going to look at that today. So we can build this up, first of all, just looking at a single collection. And we can write this in an analogous way as we just did with filter. So instead of having the predicate in, we can just cons the result of applying the function to the first item in the collection to the result of applying the function to the rest. And we're going to carry on with this whilst there are items in the collection, and then pass that to lazy seek. So this works. We can also extend it to two collections. So adding in the arity where we have the function and two collections rather than just one. And we can say whilst there are items in both of the collections, so when seek C1 and seek C2 are both true, because with map we're going to carry on until one of them is empty. So whilst there are items in them, we're going to cons the result of applying the function to the first item in the first collection and the first item in the second collection to all of the other map results to come. So this works. And we could carry on building this up. So if we had 3 collections, we could put in an error in C for that, etc., etc., apart from etc. and etc. can go on a long time. So how about building this up recursively for more arguments going in, for more collections? So we can take a look at this. So where we pass in 2 collections and a collection of more collections. And we can have a recurse point here where we set R as this collection of the more arguments coming in, the more collections coming in. And we're going to carry on until there are no more arguments. So we've just got the first 2, at which point we can return calling our function, our myMap function, with the function and just the first 2 collections. And until then, we can just apply the myMap with the function over the first 2 collections and have the result of that being the first collection. And then we iterate through the rest of the collections to come. So we're just going to be applying myMap to 2 at a time and going through. So this can work. And had tests that this passes with. So it's fine. It's just going to go through 2 by 2, going through. Which is fine until we start looking at non-commutative functions. So, such as this example where we're trying to apply vector across this vector of vectors. So this should result in mapping the first items of each, so A, D, and G, to vector, so we get A, D, and G out. And then the second items, B, E, and H. So we end up with our 3 vectors there. What happens, though, when we use this function? It fails because we're just applying to the first 2, so we get a vector AD, BE, CF, and that's then applied to the rest to come. So we end up with a nested vector. So we have the first one, rather than just being a vector ADG, it's going to be a vector containing a vector AD and then G. So it's not the result we want. And again, this comes down to the fact that we're not actually doing what we need to do. We're not building this up lazily. So how can we do that? And we're going to start, just in English, what is it we want to do? And what we want is to take all of our input collections and we can put them all in one big collection. We can then reorder the sequence because what we want is a collection containing all of the first elements, and then another collection containing all of the second elements, next collection containing all of the third elements, etc. And if we've got that reordered collections, so all the first elements together, all the second ordered elements together, we can just map the result of applying the function across each of those reordered collections in turn. So rather than just going through the collection as we had it, if we reorder them, we can just map each one in turn. So how do we do this? So first part, if we just pass in the function with one collection and then this collection of others, we can make our single collection just by consing the first collection into all of the others. So we end up with a single sequence of all the collections. If we pass this to some function called reordered, which is going to reorder all of these, so we have all the first items together, all the second items together, we can just apply our function across each of those in turn. So we can map applying the function across each of those, and that will give us the result. So what does this reorder function look like? We want to do this whilst there are items in in every one of the collection, because we know that map only goes on until one of the collections is exhausted. So when everyone is seekable, so when everyone has got an item in, what we want to do is add the result of applying my map to all of the first items in the collection. We want to add that to what happens when we reorder all of the rest. So we've got this reorder function that is going to get all of our first items together, etc. And then we can just map the results applying the function across each of those in turn. And because these two functions are mutually recursive, we need to declare one of them at the top so that they know about each other and can work through. So this works, and this then works for all the functions, including the commutative ones. So that was map. And the last one that we're going to look at is parallel map, pmap. So this is like map, except for the function is applied in parallel. So this is only of use for computationally intense functions. So functions where the time it takes to do the computation is more than the expense of setting up the parallelization. Talks about being semi-lazy, and we'll look at what that means as we build it up. So I didn't want to have a computationally intense function. Instead, I just wrote one where we put a sleep in. So we sleep the thread for 1,000 milliseconds. So we've got this long-running job function, which can take in any number of arguments. We're going to sleep for 1,000 milliseconds, and then we're going to apply a function to that argument. So when I was first doing this, I just applied the addition of 10 across all of the collections. When I started looking at other collection types that can go in here and other type of functions, I can make this just apply list to it, and then it can deal with any different type of function and collections that you throw at it. So we've got a long-running job. We can test that this does actually sleep as we want it to. So just testing this job, we can let st, so the start time, be the system time at the start. We call our long-running job, in this case just with the number 1. And then we stop the clock at the end and just adjust it to convert the time into seconds. And so we can assert that calling the long-running job should take longer than 1 second, because we've got the 1 second sleep plus the execution time. And that works. That's fine. So that function works. So what happens if we map? So we're just using the Clojure map function. If we map that long-running job across a collection, so in this case a vector 1, 2, 3, 4. So we can assert that this is going to take longer than a second. And in fact, we'd expect this should take longer than 4 seconds, so a second for each element as it iterates through. But this isn't actually the case. This fails. And it fails because it actually just takes a fraction of a second. And again, it comes down to the fact that map is lazy. So we're not actually measuring the time it takes to execute the function. We're just measuring the time it takes to form that new lazy seek, which doesn't take long. So the test fails. So in order to get this to work, we need to make sure we evaluate that long-running function every time we call it. So we can do this by, I just pulled out into a separate function, our testing time, rather than having it in the test. Again, we're going to set the start time, and then we're going to apply realize lazy seek function to our map type, so in this case map, with the function and the collection. And the realize lazy seek is going to take in those arguments, so the map type, the function, and however many collections, and it's going to set a recursive loop, so where result is applying map function with the collections, and it's going to iterate through this and call the result. So when there's a result, so this calls it, so it's actually going to realize that lazy seek. and then it will recurse through. So it will go through and make sure that we're actually running that function rather than just the lazy seek. So that gets the map to work, and it does indeed take greater than 4 seconds. So now we can actually start looking at building up our PMAP. So if we pass in the same collection to a long-running map, we expect that this will take less than 1.1 seconds, as an example. So each of these will take a second if they're run sequentially. If we run them in parallel, it should just take a second plus the bit of overhead time. So less than 1.1 seconds. So how do we build this up? So we can imagine that we can just use the Clojure futures. So this enables us to execute things in parallel. So we can apply the future of calling the function on each item in the collection in turn, and map through that. So this will give us our collection of futures. And those futures can then be run across the available threads, and we can dereference them by calling deref. So we can take our collection of futures, and then we can apply deref to it, and map that to give us our collection of results. So this looks like it may work, but it doesn't. This fails. And it fails because all we're doing at the first point when we're setting up the futures is we're setting them up in a lazy sequence, but we're not actually generating them. So we're never starting off those futures. And we're only ever calling them when we call the deref on them. So as we're iterating through, we start our futures at the same time as we then call them. So in this way, we end up just taking as much time as we did with map. We generate a future, and then we're blocked until we get the result through. So how do we move this in order so that it works? Well, we need to generate all of the futures first before we try to deref them. And we can do this using the trick that actually tripped us up earlier when we were using conj, because conj isn't lazy. So this means it's going to evaluate the results as it goes through. So now we can apply our function to the collection still, but as we do that, we can conj that into a vector. So because we're applying conj, we're going to generate that future as we go. So we can use our reduce function. We're going to iterate through our collection and return a single value, and this value being a vector containing all of the generated futures of the results. So now, at the start, we generate all of our futures. They can all run in parallel, and then we can just map that collection of futures to the collection of actual results by dereferencing them with deref. So now these are actually running in parallel, and our test works. And we can extend that test to other collection types, and we can extend to more than one collection in exactly the same way as we did with map. So now this behaves the same as the core PMAP does, and we use that trick of conjing to realize the futures so that we can have our semi-lazy PMAP implementation. Just as the same with all of the other functions, we can use property-based tests to confirm that our function are giving the same results, behaving the same as the core functions. So, given this, how do we feel about taking that base jump? So when you take a skydive, you've got a long way to go, so you've got enough time in order to get up to terminal velocity. We're more stable when we're at terminal velocity, so we can have a more stable parachute deployment. So things are fine. That's not necessarily the case with a base jump. You're jumping at lower altitude, you don't have enough time to get to terminal velocity, which means you're less stable. So you have to make sure that your input into the jump is very steady and prepared, and you can deploy carefully without going back into the building or hitting other people. So you need to really know your equipment. Your equipment needs to be correct for the job, for deploying at lower speeds and for slowing you down quicker. And you need to make sure your input into the jump is well executed, because if you don't start steady, you're not going to be able to steady up in time in order to deploy. So it's the same in the code. When we jump into things, we need to make sure we understand the inputs and understand the function, how it works, so that we don't get tripped up and take that jump into using the function when it doesn't actually work as we wanted. So I urge you to go and have a look in whichever language you work in, implementing your own versions of some of the functions, really understand how it all works, and use that to make sure that you understand every line of code as you're moving forward with your work. So, thank you all.